Hello guys, welcome back to today's question, which is going to be cousins in binary tree 2. Alright, so here's the question. So you're given a root of a binary tree and should replace the value of each node in the tree such that it is the sum of its cousins' values. Right, so in this case, two nodes of a binary tree are known to be cousins if they have the same depth but different parents. So let's explore that using this example, right? So we have the root of the node, root of the tree, which is 5, and notice that it has no cousins, right? So it has no cousins. And as for node 4 and node 9, you notice that they have no cousins as well. They only have siblings, right? Sibling of 4 is 9, the sibling of 9 is 4. And in the third depth, the depth is now 2. Depth here was 1, depth here was 0. So you notice that 1 has a cousin which is 7, 10 has a cousin which is 7, right? And 7 has cousins which are 1 and 10, right? So they all have the same depth, but they have different parents, right? Like 1 and 10 have 4 as parents, and 7 has 9 as parents. So let's see how they formulated the resulting tree here. So we know that 5 has no cousins, so the total sum is going to be 0. And 4 and 9 have no cousins as well, so they're also going to be 0 on both of these nodes. And if you look at this node, which is 1, you notice that it has one cousin which is 7, so the value is going to be changed to be 7. A similar way can be used to explain this node, which is also going to be 7, as it has a cousin which is 7. And as for this node 7 here, you notice that it has two cousins which have values 1 and 10. So 1 plus 10 is 11. That's how you get 11 here, right? So let's see how we can go about solving this problem, right? So if we look at at a way to, if we look at how we can approach this, we can approach it by using level order traversal. As we notice that we need to identify the sums and the values at each specific depth, one way we can go about doing it is using a level order traversal with a queue, so that we can go through each depth at a time. Moreover, at each depth that we go into, we need the total sum in this depth, and then the sum of a node and its siblings if there are any, right? So let's look at this example, right? At the bottommost layer here, the total sum in the layer is going to be 7 plus 1 plus 10, which is 18. And as for this node, it's going to be 18 minus 1 minus 10, right? These are the values of itself and its sibling. So 18 minus 11 will give you 7. A similar way can be used to explain this node. And as for this node, it's going to be 18 minus 7, right? There's no other sibling node here, so it's just going to be 18 minus 7, which is going to be 11. So now we know that all we need to do is look at each layer, count the total number of the total sum of all the values of all the nodes in that layer, and then for each node just subtract away its values and its siblings values. So if you do that, then you will get the correct cousin count. Now we'll go through the main while loop of how we can perform the level order traversal, right? So first we initialize a variable called TOT, which is going to be the sum of all the nodes values in the current depth, right? So in this case it was 18, here would have been 13, and here would have been 5, right? We also initialize an array called children, which is going to contain all the children in the current depth, right? So which is going to be 1, 10, and 7. Right, so we iterate through the length of the DQ, right? So when we are trying to figure out what are the sibling sums, the total sums for this depth, we will currently be analyzing the nodes at this depth, right? So we pop the element, which would have been 4 or 9, let's say 4 in this example, right? And then we can first change the value, right? So lm0 dot value is going to be lm2 minus lm1, which is what we've done above, as you can see here. This will ensure that we can fix the values properly, right? So in this case, let's look at this node 4, right? So we would have noticed that lm would have been equal to node 4, then 13, and then 13, right? So, and then in that case, cos 13 is the sum of the siblings, 13 is the sum of the entire layer, say the entire depth, which was 4 plus 9, right? So, and then you get 13 minus 13, which is going to be equal to 0. So lm0 dot value is going to be 0. So that's how we can kind of like fix the value of the node 4, right? And then we also initialize a sibling sum, right? So now we know that for node 4, it's possible for it to have a left child and a right child, right? And we need to find what the total sibling sum of both these is, right? So we initialize two Boolean flags so as not like repeatedly add left and right child sums, right? If node 4 has a left child, then sibling sum was going to be the left child's value. So right, it's going to be, now it's going to be 0 plus 1. So it's going to be 1, right? Sibling sums at this point is going to be 1. Right, and then we set the Boolean flag for left to be true. And then if 4 also has a right child, then we set right flag equals to true, and we add the right value. So 4 plus 10, which would 1 plus 10, which would have given us 11. Equals to 1 plus 10, which brings us to 11. Right, so when we do that, now we know the sibling sum for both the left and the right child, right? And we also add the left value to the total, right? The total was initially 0, so now the total is going to be 1. And we initialize an array. So notice that in each DQ, right, every element has 3 values: the node, the sibling sum, and the total sum, right? So currently we don't know the total sum yet, right? Because we haven't processed this node yet, right? So we just set the array to be the node plus the sibling sum, because that's all that we know that is sure at this point in time. And we append this array to children, right, which we initialized earlier. A similar way for the right side. So if lm0 dot right, and if the right has not been added yet, we add to the right side to sibling sum. And if it has a left side and the left has not been added yet, then we append the left value to sibling sum. So this will ensure that we don't repeat sibling sum additions. After that's done, we add the right value to TOT, right? So now TOT is going to be 1 plus 10, which is going to be 11, right? And then now we have AR, which is going to be LM right sibling sum, and we append this to this children array that we created earlier. So after we go through all the children, right, so which is pretty much like this for loop in this scenario here, you will get an array which is children, which is going to be populated with all the nodes, sibling sum, and that's it for now, right? So this is going to be a bunch of stuff like that, right? So for every, and now as we have covered all the elements in this depth, you know, notice that the total sum is now been calculated correctly, which is going to be 18, right? So of course we processed 1, 10, and 7, so now it'll be 18. So after that is done, then we iterate through every element in this array, and we append the total to it. So now each element in the children array is going to be of the form like this, right? So node, sibling sum, and then TOT. So this will enable us to, let's say in the next depth, we can perform this operation, right, where we modify the value by lm2 minus lm1, which is total sum minus sibling sum. So after that is done, we proceed on to the next layer, and then the next layer until the entire level traversal has been completed. And then return the root at the end of your operation. So that's how we ensure that all the values are updated to what their sibling sums are. So with that, that's the end of the code. And as for time complexity, it's going to be linear as well, as we process each element in the node at most like 2 times, right? Because there's this one for loop here. There's also this one for loop here, which is the children array, right? So it's going to be on. And as for space complexity, it's going to be linear as well, as we are using a double-ended queue. And yeah, so it's going to be linear as well. So that's it for today's question, and hope you enjoy watching. Thank you.